So continuing in our trig, I realized that we haven't talked about the trig functions as functions yet. So let's take a look at how we write those. So from the unit circle, we have cosine theta comma sine theta. And so using these, we can write down the values. This is theta, and so this would be your y, which is cosine theta. Okay, and so from our graph here, remember that the cosine is the x-coordinate. So if we start here at theta equals 0, then our cosine value is 1, that's x equals 1. And then what does the x-coordinate do as you rotate counterclockwise on the circle? Your x-coordinate decreases, okay, until it gets to -1 at the value pi. So if we go to pi, and so at pi over 2, we see that what happens, x is equal to 0, right? So x goes from 1 to 0 at pi over 2, that's up here, and then goes down to -1 at pi. And then we just reverse, right? So we're continuing to go in this direction, and so the x-coordinate is going to come back up, cross the x-axis again at 3 pi over 2, and then come back up to 1 at 2 pi. 2 pi. 2 pi. Okay, so this pattern just repeats itself over and over again. So we say that the period of y equals cosine of theta is 2 pi. That means it repeats every 2 pi units. Okay, so similarly, if we were to graph the sine function, we start at 0, that's the y-coordinate. Then as we rotate counterclockwise, what does the y-coordinate do? The y-coordinate increases, right? So we start at 0, the y-coordinate increases to 1, and then as we continue across, then the y values go down, right? And then it comes back up at 2 pi, so this is pi. And so this is a very symmetric graph, by the way. Right, so there's a symmetry here between these here and here, okay? So you can assume that. Good. And so then the sine of theta is periodic as well. Period 2 pi. Good. And so finally, what happens to the tangent function, which is sine over cosine? Well, if I graph the cosine here, oops, I'm keeping it dotted because if cosine of theta is in the denominator and the denominator is 0, we're going to have a problem, right? And so the tangent function actually has vertical asymptotes at plus pi halves and minus pi halves. And then in between, we're going to verify this later, it looks something like this. Right? Remember, the tangent of 0 is the sine of 0 over cosine of 0, which is 0 over 1. Okay, so it goes through that point. Good. So what you're seeing here is that this graph is going to be repeating itself now every pi units, and so the period of the tangent is pi. Good. Okay. Let's see. I guess we're not going to have to graph the secant and cosecant and that kind of thing. They are nice to know. They're kind of fun to draw. But one other thing I just wanted to point out were some identities before we look at some identities. Oh, my penmanship is terrible today. It's hard to write on these tablets. Identities. So our Pythagorean identity is the one we use the most. sine squared theta plus cosine squared theta equals 1. Some other ones that we're going to use often are the double angle. And so that's sine of 2 theta is equal to 2 sine theta cosine theta. And then cosine of 2 theta has multiple representations. Well, I'll just write down that cosine squared theta minus sine squared theta is probably one of the most popular ones. Now to prove these, the typical way to do that is through a sum and difference formula, which is on your cheat sheet, but I'm not going to ask you to prove it. Sometimes the sum formulas are nice to know. Yeah. Oh, by the way, when we look over here at these three functions, you'll notice the domain and range. Domain of cosine and sine are all real numbers, and the range is just between -1 and 1. Okay, let's see, I'm just looking over that trig cheat sheet before we take a look at a couple more problems. Good. Okay, so let's take a look at a couple of example problems, exercises. 1. Graph the absolute value of the cosine of x. Okay, well, the main thing to remember about the cosine is that it starts at 1, and then you have this nice repeating pattern. And the repeating pattern takes 2 pi units, so therefore you can, from there you can write down the other values. So this would be minus 2 pi, right, minus pi. Okay, so this is the regular cosine. Now if you want to plot the absolute value of the cosine stays the same when the cosine function is positive. What happens when the cosine function is negative in this region? Well, the absolute value turns these values positive. Okay, so the red curve then is the absolute value of the cosine of x. See, isn't that fun? All right. How about something like, how would you compute the inverse tangent of 1 over the square root of 3? So you might recognize this, right, as one of our special triangles. So I would just go ahead and just jot down the triangle if you don't remember it. Right, this looks like 45, 45, but it's actually 30, 60, 90 pi 6 pi thirds. Now this is 1, 2, square root of 3. Which side it goes where? The 1 goes opposite pi 6th, so that leaves square root of 3 and 2. Right, so which angle gives you, let's go ahead and write this as tangent, or theta. So by answering this, we want theta so that tangent theta is equal to 1 over the square root of 3. So which theta is it from the triangle? Opposite over adjacent pi 6th. Good. You'll see a few more of that style on the homework, but I think I'm going to stop there and let you work through some of the exercises. All right, see you later.